Hey guys, Mr. McKinney here, picking up on part 3 of our Unit 9 review series. So we're working on the chain rule now. So basically, if you have a function as the upper limit, you plug that function in, and then you multiply by the derivative of that function. So let's look at a couple of examples. All right, got capital F, trying to find lowercase f, so I need to take the derivative. So capital F prime of x, which is little f of x, would be the derivative with respect to x going from pi over 2 to x cubed cosine of t dt. Everything's in the right place. Everything matches the way that it's supposed to. This variable matches, that variable matches, and I have a constant. So I can just plug in x cubed, but then I need to remember to multiply by the derivative. So if my g of x is x cubed, g prime is 3x squared. So I need to multiply by 3x squared at the end. So cosine of x cubed times the derivative of x cubed, which is 3x squared. Now, if there's more than one t in this equation, so if it had been something like cosine of t plus sine of t, you plug in x cubed into both places, but then you would just multiply the whole thing by 3x squared. You don't like multiply by it twice or something like that. All right, and then this is a little bit more complicated version because you have a variable on the bottom and a variable on the top. So you're going to have to use a couple of different techniques. So the first thing you're going to want to do is split it up, say x to whatever number you want, plus that same number to x squared. You can pick whatever number you want. A lot of times 0 is easy to work with. As long as it's the same number, this is a rule that you're allowed to use with definite integrals. This is a property of definite integrals. So secant squared of t dt, secant squared of t dt. This one's in the right form, so when I take the derivative, going down to little f, this one I can do from here. I just plug in x squared, so it's going to be secant squared of x squared times the derivative of x squared, which is 2x. On this one, I can't do it yet because the limits are in the wrong place. I need the constant on the bottom. So before I would actually take the derivative of this, I would rewrite it and put a negative out front and switch the limits. Sorry, secant squared of t dt. So then when I plug in x, I would have negative secant squared of x. I don't have to multiply by anything here because the derivative of x with respect to x is 1. So just remember, if you have a function on the top, to use the chain rule. If you have the variable on the top and the bottom, split it up so that you can get constants in there instead. All right, on to 9.5, which was differential equations. Okay, so on differential equations problems, pay attention to what it's asking you to do. So this first one just says find the equation of a tangent line at a specific point. Keep in mind, anytime you're doing a tangent line equation, you're going to use point-slope form. And the nice thing about the differential equations problems on the AP exam is they almost always give you x and y. So then you just plug x and y in here to figure out what the slope is. Y prime is the same as the slope. dy dx, m, those mean the same thing. It's the rate of change of y with respect to x. So at the point 1, 1, I'd have e to the 1 plus 1 over e to the 1, e squared over e, which is e. So my slope is e, and my point is 1, 1. I'm done. Y minus 1 equals e times x minus 1. Don't worry about solving for y unless it's multiple choice and all the answer choices are solved for y. Now, make sure you get the easy part of the differential equations problems on the AP exam, because there's usually an easy piece and then a more challenging piece. A lot of times the tangent line equation is the easy piece, so don't overthink it. Now, if it wants a particular solution, this is where I need to separate the variables. And when I'm talking about a particular solution, the slope field itself, or this differential equation, gives you all the different possibilities. And then we want a particular solution. So we want to pick a specific one that goes through this point. So let's visually think about what we're doing here. This slope field would look something like this, and we're talking about the point 1, 1. So the slope field represents all of the possible solutions to this differential equation. But now I want to know the one that goes through this point at 1, 1. So what curve is going to go through and then follow these slope marks? So that's what I'm trying to figure out. So I have to separate the variables first. Make sure you guys get good at this step, because if you screw this step up, you can't get any of the other points on this type of a problem. So dy dx equals e to the x plus 1 over e to the y. Separating the variable means make sure you get x and dx on the same side, y and dy on the same side. Now you could cross multiply here, or you can multiply both sides by dx and multiply both sides by e to the y. Doesn't matter. So you're going to get e to the y dy equals e to the x plus 1 dx. Make sure you're always putting your dy or your dx at the end of the expression. Now I'm going to integrate both of these. E to the y equals e to the x plus 1 plus c. You could use u substitution here, but a lot of you guys will be able to do that without your head, or do it in your head, since the derivative of x plus 1 is just 1. Make sure you get your constant in at this step. Before you go any further, solve right now. So e to the first equals e to the 1 plus 1 plus c. So e equals e squared plus c. So my constant would be e minus e squared. I'm not done. Now I need to plug that in. So e to the y equals e to the x plus 1 plus e minus e squared. Now to get it out of the exponent, I need to take a natural log on both sides. So natural log of e to the y equals natural log of e to the x plus 1 plus e minus e squared. Now I can move that y in front. Ln of e is just 1, so that whole side just becomes y. So ln e to the x plus 1 plus e minus e squared. So particular solution or specific solution is going to use your initial condition to find the c value and then find the solution. Technically, I could have stopped here because it doesn't say anything about the function y equals f of x. But a lot of times on the AP exam, it'll say find the particular solution y equals f of x. That's what tells you that you need to solve for y, if you see that statement on the AP exam. All right, there's one other specific type of differential equation that pops up more often than other ones. And this is going to lead into 9.6, which is exponential growth. So if the rate of change depends on the amount that you have, this is basically exponential growth. So this just leads into the next unit or the next topic. So you still want to separate your variables first to find a particular solution. So dy over y equals a dx. When I integrate, dy over y becomes ln absolute value of y. When I integrate a with respect to x, I'm going to get ax plus c. Now, I think it's easier to, well, let's solve for y first. Since I have 2 points, well, I can pick either of them to find my c value. So let's find c real quick. Oh, wait, no. We're going to have to set up both of them because we need to find a and we need to find c. So I'm going to set up both of those equations off to the side. So ln of 50, I don't need absolute value anymore, equals a times 0 plus c. And then ln of 100 equals a times 5 plus c. Now I'll be able to find c from here because a times 0 goes away. So c is ln of 50. So then ln of 100 equals 5a plus ln of 50. I can subtract that over. So 5a equals ln of 100 minus ln of 50. So 5a equals ln of 100 over 50. So 5a equals ln of 2. And a would be ln of 2 over 5. So now that I know a and c, I can plug them both in. So ln absolute value of y equals ln of 2 over 5x plus ln of, sorry, c is ln of 50. Again, it doesn't say that we have to solve for y, so we wouldn't necessarily need to. To get it out of the log, you would put it into an exponent, so ln 2 over 5x plus ln of 50. Now, you can rewrite this. So first of all, an exponential is always positive. If we think about the graph of an exponential, it's always going to be positive. So we don't really need the absolute value here. So we can say it's e to the ln of 2 over 5x plus ln of 50. Now it might stop here, or you might see some exponent properties going on. So you might see something like e to the ln of 2 over 5x, and then instead of adding in the exponent, you can turn it into multiplying. So e to the power of ln of 50. E to the power of log base e of 50, this whole thing just becomes 50. So I can rewrite this as 50 times e to the ln 2 over 5x. Now, if you recognize, since this is the review video, we already know the formula for exponential growth. Y equals y naught e to the k t, or in this case, e to the kx. K, in this case, we called a, but sure enough, it popped in there in the exact same spot. Y naught, we didn't call it y naught, we said y of 0, but those mean the same thing. So this leads into 9.6, which was on exponential growth and decay. The video series for this one is fairly short, so I'm not going to spend too much time on this. If you want help on exponential growth and decay, just go watch those 2 videos again. The important thing to keep in mind is that you're either going to see this statement that y changes proportionally to the amount present, or y changes proportionally to y, or the rate changes proportionally to the amount present, or this differential equation, dy dt equals ky, or dy dx equals ky. So the rate of change of y depends on y. So if that's what you have either in words or in a differential equation, in your brain, that needs to tell you that you're going straight to exponential growth and decay. To see how to get from this equation to this equation, it's basically the same thing we did right here, or you can go watch the 9.6 videos again. The rest of 9.6 was just word problems with examples of exponential growth and decay. So just go back and rewatch those videos if you need help on those concepts. Main thing to keep in mind is you're looking for rate proportional to the amount present, or dy dt equals ky, or dy dx equals ky. The d variable on the top should match the variable that you're being multiplied by a constant on this side. All right, hope that was helpful. I know this video series was kind of long, so hopefully it was beneficial. See you guys later.